Hey guys, so I'm going to do a nice easy lesson for you today on Simpson's rule, which I guess I should actually remind us is actually from FP1. Okay, so this is an FP1 numerical methods Simpson's rule. Okay, this is the last part of numerical methods from FP1, and for this, it's basically about another technique for doing something numerical to estimate the area underneath curves. So I've written here, Simpson's rule is a very good estimate for the area under a curve, and the way that it does this, it's different to the trapezium rule, which estimates them all as trapezia. Instead, it estimates by using parabolas. So you'll see here, each of these sections are all different parts of parabolas. And the idea with doing this is, in theory, it should create a better fit for a curve. There must be an even number of vertical strips because it's the pairs of strips that make up the parabola for that section. So if you see here, if you couldn't end, let me say what I'm saying again here. Let me just quickly grab a highlighter. So you can see this section here is one part of a parabola. This section here that's in the red part is the parabola. So maybe I should actually switch that around a second. This red section here is a parabola, and last of all, this red section in the middle, which I'll do in this sort of blue colour, is a parabola. So now it kind of makes sense why there needs to be an even number of strips, because each pair creates a parabola. It's not each section, it's the whole curved bit. So again, you can see here, this is a parabola, this is a parabola section, and this is a parabola section, and each one is made up of two things that you've got. You'll also see on this one again, you've got a parabola here and a parabola here. That's why there has to be 4, 6, 8, any even number of strips. So here is a picture of Thomas Simpson, the British mathematician who was alive in the 18th century. And the way that we use Simpson's rule, where there are 2n strips of width h, so here this is 6 strips, so we would say that n is 3. To try and find a rough numerical approximation of the integral of the curve between a and b, I'm actually just going to read out this version that we have here. You do a third multiplied by h, where h is the gap between them. So in this one, the value of h would be 0.5. And then you have the endpoints, 4 times the odd values and 2 times the even values. So just to kind of point out what that would look like, in this one that I've got up here, these are the endpoints. The odd values are these ones, and then the even values are these ones that we have here. Okay? The reason that you get 4 times the odd values is because they're used 4 times. So they're used once for this parabola. I just said because they're used 4 times. I can't remember the exact reason for why this works actually. My apologies there, guys. But it's because the odd ones are being used more because they're at the bumps of the parabolas, whereas the even ones are on the end part, so you have them like this. The way that I remember this is because I know, and this is such a random way of remembering it, when we didn't have the pi button on the calculators, I would remember pi, and it was 3.142. Okay, 3.142, that's pi to 3 decimal places. So this is my memory for this, because this one doesn't actually come up in the formula book. The 3 reminds me of the fact that there is the third at the beginning. You then get 1 for the endpoints, and we know the endpoints come first because that's the one that's on the end. Then the odd values goes with 4 because we've got odd ones coming up afterwards, and then the even values are 2. So that's my way of remembering the 3.142, in fact the third 142, because pi is 3.142. Just to show you what this looks like as an animation, so here we're trying to work out the area underneath the blue curve, which is clearly some kind of sinusoidal curve. And the red bits that you should notice are all different parabolas. And you'll see to begin with that there's this big kind of bump of a parabola, and then there's 2 separate parabolas as we increase the number of strips. Always the number of strips is even, and the more strips that you have, you can see how well it fits the particular curve that we have here. So I'm actually just going to do one example on this because it's just about using the formula, and then I think that you guys should be good to do this last part, and I'm just going to leave you with this amount of work to do today. So I've got a reminder of what the formula is up here, and we're going to use Simpson's rule with 4 intervals to estimate this particular thing that we've got here. So it's going between 0 and 2. So that's going to make us think about what the gaps are going to actually look like. We're going to have our values of x here, and we're going to have our values of y along here like this. Much harder to draw my straight lines here. And we're going to start with 0. If they want 4 intervals, you're going to just divide it by 4. So we're going to have 0, 0.5, 1, 1.5, and we're going to have our 2 that we have over here as well. Okay. So when I put in 0, I'll just substitute straight in. I'm sure you all know how to do this in your calculators, but you should remind yourself that you can actually just put it in a mode that generates the things that you need for you. So I'm just going to put mine into the calculator. I'm just going to do it as my, e to the minus x squared. So that's e to the minus x squared plus cos x and plus 1. So I'm going to generate the values that I've got. I'm going to start between 0 and 2, and I'm going to go up in 0.5s. So I have, this one is a 3. This one is a 2.778. I'm going to go for 4 decimal places here. This one is 2.3677, 2.3677. Check you've got the same as me, please. This one is 2.1051, and this one here is 2.0177. Okay, so let's just remind ourselves about how we're going to use this formula. We know then that the approximation of the integral, why have they gone for red? I don't want red. Let's just erase this for a second. Okay, I'm going to integrate between 0 and 2 of my f of x dx, I couldn't be bothered to write that out again, is just going to be a third multiplied by the height. Now the height in this case is 0.5, and we're going to multiply that by the endpoints, which are these two. So that's 3 plus 2.0177 plus 4 multiplied by the odd values, which are these ones here. Remember, it goes x0, x1, x2, x3, x4. So I've got my endpoints and my odd values. So my odd values are 2.7788 plus 2.1051. And then you're going to have 2 multiplied by the even values. Well, in this case, I've only got that last even value. Don't use the endpoint. You've already used the endpoint. You've only used them once. So that's 2 times 2.3677. Now, because I've done all of these to 4 decimal places, I'll probably give my answer to 2 decimal places so that I've got some level of accuracy there. So let's just quickly go back to my calculator. So that's a third times 0.5 multiplied by, let's just type this all in. So it's 3 plus 2.0177 plus 4 multiplied by 2.7788 plus 2.1051 plus 2 times 2.3677. Close off the brackets, and I guess I really should have done that this was approximately equal to, because it's not going to be exactly equal to this, it should be approximately equal to 4.88145. So I'm just going to stick with that to 2 decimal places. I'm just going to say that it's 4.88 units squared, and that is to 2 decimal places. Okay, so this formula is not given to you in the formula book, but remember, it is a 3 at the beginning because of the 3 part of pi. Is pi 3.142, and you're going to multiply it by the endpoints plus 4 times the odd plus 2 times the even. 3.142. That is my way of remembering that formula. I don't like trying to have to remember it like this. I definitely don't like having to try and remember this kind of thing, which is just kind of crazy and a bit unnecessary. So we can now finish off that part of numerical methods for FP1. So you can try exercise 8D. I've got some questions here, but really at this stage you can try any of the ones that we have. I think B and here there might be some proof kind of questions, which we probably don't need to have a look at right now. Okay guys, speak to you soon. Bye.